today Andrés Chirre from Norwegian University of Science and Technology is going to talk about the behavior of the argument of the Riemann zeta function.
Okay, so thank you so much for the organizer for this opportunity to talk today. Today will be my first talk by Zoom, so I don't know if it will be long or short, so please stop me if I am in the time. So today I would like to talk about the behavior of the argument of the Riemann zeta function. And the idea is to see some results related with the argument of zeta. Let me start talking something about the Riemann zeta function. So we know that zeta is defined a series in this form, the series 1 over n power s, where s is a complex number and it is defined in the semiplane real part s bigger than 1. We know that this function has this Euler product too. Finally, we have this function defined on real plane, on the semiplane real part s bigger than 1, and we can extend this function as a meromorphic function over the whole complex plane with a pole in the point s equals 1. And one of the questions about this function is the zeros. Where are the zeros? For instance, in real part s bigger than 1, we know that there are no zeros. Using the functional equation, we know that there are simple zeros. There is trivial zeros. This is the correct word. In the semiplane real part s smaller than 0. And the question is, in this strip between real part s 0 and 1, where are the zeros? And one of the famous conjecture is done by Riemann that say all non-trivial zeros of zeta have real part equal 1 over 2. So there are on the line 1 over 2. Let me start talking about this beautiful proposition about the number of zeros of zeta in this rectangle here. So Riemann-von formula states that the number of zeros in this rectangle has this form: t over 2 pi log t over 2 pi minus t over 2 pi plus 7 over 8 plus this special function plus an error term. So today I would like to study this special function that appears here, st. This function st is the argument function, and we will define in this form. When t is not the ordinate of a zero of zeta, so you define st in this form: 1 over pi, the argument of zeta in this point, and you take this argument in this form. You take the continuous variation along this path 2 plus it, 1 over 2 plus it, starting with argument of zeta 2 equals 0. And in this path, you don't have 0, so you can define the logarithm, and you can define an argument. So you define the argument of zeta st in this form: 1 over p multiplied with the argument. Similar, you can define not just for 1 over 2, you can define for any sigma between 1 over 2 and 1. You can define here in this point sigma plus it. So I will divide the talk, if we have time, I will divide the talk in 3 parts. The first time is use band limit approximation to obtain bounds for st. The second part is to use the resonance method to obtain omega results for st. And finally, if we have time, we will show extensions of these results for functions called SNT. We start with band limit approximations. So a classic result of Littlewood in 1924 state that assuming Riemann hypothesis, st is bounded in this form. This bound is a constant plus an error term that's going to 0, multiplied with log t over log t. The idea now is to optimize the value of the constant here, if we can put a good C in this part. So we have some results related with this. This is the inequality given by Littlewood. And for instance, Ramachandra and Sankaranarayanan in 1993, he established this constant 1.118. Fuji improved these results with a constant 0.67. Golson and Gondek improved this result with a constant 0.5. And finally, Carneiro, Chandel, Milinovich obtained a constant 0.25, 1/4. Really, in 2012, Carneiro, Chandel, Milinovich give two proofs of these results in this form, where this error term has this form. Later, in 2015, Carneiro, Chandel, Milinovich give a new proof of these results. And finally, with Carneiro and Milinovich, we give a new proof of this result again, 1/4, but we give an improvement in this error term with the form 1/log t. So let me give a sketch of the proof of this result, 1/4 plus this error term multiplied log t over log t. So I will start defining two special functions. I will start defining for sigma bigger than 1/2 and t positive, the function s minus sigma t. That is the derivative of the argument function in the point sigma plus it. We remember that the argument is the imaginary part of a logarithm. So when you take the derivative, you obtain 1/pi real part of zeta prime over zeta at the point sigma plus it. And we define the function s1 sigma t as an integral of s plus a special constant. And we use these functions, and we obtain bounds for these functions. And using these bounds, we obtain bounds for the function s sigma t. This is the idea here. Well, we want to obtain bounds for s minus 1 sigma t and s1 sigma t in these steps. First, I would like to obtain other representations for this function, s minus and s1. In this representation will appear certain sums over the zeros of zeta. And to try to understand this sum, I will use explicit formulas to evaluate these terms. But we will see that there is a problem to use these explicit formulas, so we need to go to Fourier analysis to obtain special functions, to find special functions called majorands and minorands, and try to use this explicit formula with these terms, and we can obtain bounds for s minus 1 and s1. And using an argument of interpolation, we can obtain information about s. So, assuming Riemann hypothesis and using, for example, Hadamard factorization, we can obtain that s minus sigma t, we know that is the real part of zeta prime over zeta. You can obtain that has this representation, 1/2 pi log t over 2 pi plus 1/pi multiplied with a certain sum that depends of the ordinate of the zero of zeta, evaluate certain sum in a function evaluate in t minus gamma. And this special function here is the Poisson kernel, sigma minus 1/2 over sigma minus 1/2 power 2 plus x power 2 plus the error term. This is the first step for s minus 1. For s1, we can use again some things in another representation for s1 in this form. This term, this again, this special sum over the ordinate part of the zeros of zeta, evaluate of the function f, evaluating t minus gamma, and this function f1 sigma is defined in this form. And let me move this part. Okay, and okay, using some machinery in analytic number theory, we can obtain this representation. But now the problem is to understand these sums that depends of the ordinate of the zeros of zeta. And it is of f evaluated in t minus gamma. To obtain the behavior of these sums, we have this explicit formula, Ginn and Weil explicit formula. And it's a assume Riemann hypothesis in this case, and assume that you have a beautiful function, a nice function, HS. When I say nice function, I mean it's a function, analytic function in some strip with some decay. If you have this special function, that's this sum over the ordinates of the zeros of zeta of the function h evaluated this gamma. Well, in our case, we have t minus gamma, so we just need a translation here to obtain this part. And then we can obtain these terms depending of the gamma function, the function h, and this series here that depend on the Fourier transform of h of our nice function, and other terms that in our case will be error terms. So we don't have problem now with these terms. Okay, so I would like to use Ginn and Weil explicit formula here to replace this sum with this integral and this sum. But we have another problem because this function Poisson kernel and this function here are not nice functions. This is our problem now. So what is the problem exactly? We have an object s minus 1 or s1. We have this representation. This object is some function plus certain f in t minus gamma plus the error term. This is the problem now. But if we want to understand this sum, it will be very nice if we can replace this function f by a function h. And this function h, if this function h is a nice function, so we can apply Ginn and Weil explicit formula. This is the idea. And other condition that we want to have is the following. This is a series, so it will be very nice if we can truncate the sum of if we can have just a finite sum. It will be very nice if we can have finite sum here. So I would like to find a special function h such that h is bigger than f, and then the Fourier transform of h has compact support. In this case, this series will be a finite sum, and I can evaluate. So this is the idea, to find a function h with that, well, find a function h bigger than f such that the Fourier transform of h has compact support. And if we obtain this, we can use the Paley-Wiener theorem that says if you have a function with this property, the Fourier transform of compact support, so this function has exponential type, 2 pi delta, for instance, if the support is minus delta delta. So if the Fourier transform has compact support, we have a special decay for the function h. This is the Paley-Wiener theorem. So again, we have this problem. For the function f, we want to find a majorand here, such that the Fourier transform has compact support, and such that the distance L1 between the function h and f is minimal. This is a technical part here. So if you give me a function f, I will solve a problem. Berlin, he obtained the solution of this problem. For instance, the signum function. If you have the signum function and you want to find, and you have the set of functions, entire functions of exponential type 2 pi, such that fx is bigger than the signum function, I would like to find the infimum of this integral. So I would like to find the minimal of this integral. And this is a problem by Berlin, and he solved this problem. You have this signum function here, and he obtained a solution of this problem. The solution of this problem, the infimum of this integral is 1, and this function is exactly this function here. And this is the form of this function, this entire function. Selber, for instance, you have the characteristic function here, and in the set of functions such that the function is entire function of exponential type 2 pi, and you want to find the function such that is bigger than the characteristic. The idea is to find the function such that this integral is minimal. And in this case, there is a solution. There is a function such that are entire functions of exponential type 2 pi, and this integral is minimal. The answer is 1, and there are many functions that satisfy this condition in this case. So this is a classic Berlin-Selberg problem, and here we have some results about this. So for the function signum, you obtain the solution by Berlin. For the characteristic function, Selberg and Logan solved this problem. When you have the exponential function, Grammar and Baller solved this problem. Of the modulus of x, Carneiro and Baller solved this problem. In another paper, Carneiro, Riemann, and Baller solved this Berlin-Selberg problem for a big family of even functions, including the Gaussian functions and this special function that we want. And finally, Carneiro and Baller solved this problem for the big family of odd functions, for instance, this type of function. In the paper of Carneiro, Riemann, and Baller, they give these results. If you have a finite non-negative Borel measure and you have a function fx such that fx has this form as an integral of the Gaussian with this measure, so we can solve the Berlin-Selberg problem. So we can obtain a majorant of this function f. So we can obtain a function h bigger than f such that the function h has exponential type 2 pi delta. Very nice, because in our case, we are looking for a majorant of the function f minus 1 sigma, that this is the Poisson kernel, and this function has this form, an integral of the Gaussian with this measure, and this measure is defined in this form. For the other case, for the function s1, we have that the function f1 sigma, that this is this function, has again this form, the integral of the Gaussian with this measure. And this is the measure here. So this function satisfies the condition of the theorem of Carneiro, Riemann, and Baller. So we can find majorants in this case. So the idea is the following. For instance, for the function s minus 1, we had this representation lemma. Now we can change this function f, we can replace this function f by the function h. So this is an inequality here. And then we can apply the Guinan-Weil explicit formula now, because our function satisfies our condition of decay and is analytic. It's a function of exponential type. So it's analytic and has a nice decay. And exactly, we can use Guinan-Weil explicit formula here. We need to use Stirling formulas to understand this integral over the gamma function. We use the prime number theorem to estimate these finite sums now. We use some property of the majorant, h. And finally, because we have free delta, we optimize choosing p delta equals log t. So we use the Guinan-Weil explicit formula here to replace this part, We optimize using this pi delta. And finally, we can obtain this estimate. S minus 1 sigma t has. Okay, this is a majorant. Really, we can return to the problem and we can ask about minorant. And again, using the same theorem of Carnero, Lehmann, and Baller, they have another theorem where they solve this problem for the minorant. So we can obtain upper bounds and we can obtain lower bounds. The same situation appears for the function S1. We can obtain a majorant and minorant. So finally, we can obtain the following. For the function S minus 1, we can obtain this behavior, these inequalities, upper bound and lower bound. And for the function S1, we can obtain upper bound and lower bound. Okay, this is very nice for the function S minus 1 and S1. But what about S sigma t? Because this is our problem, to obtain bounds for S sigma t. Is defined as the derivative of S sigma t, and the function S1 is defined as the integral of S. So the question is, I am giving you information, I am giving you bounds for the derivative of S and for the integral of S. And the question is, can you give me information about S sigma t using these bounds? And this is exactly that we can do using real analysis. For instance, mean value theorem, we need to do some integration over certain parameter, and we need to solve two optimization problems that appear here. If you give me information about the integral and the derivative, I can give you information about the function. So finally, we use real analysis to use these bounds here to obtain this type of bounds for S sigma t. Two, if sigma goes to 1/2, S 1/2 t is exactly the function st. So we recover st here, and this function are nice because when sigma goes to 1/2, this function is 1/4, and this is exactly the constant that we need to obtain. When sigma goes 1/2, you have here 1, so you have log t over log t, and this is the bound of Littlewood. And these error terms, where sigma goes to 1/2, we obtain these error terms. So finally, we can obtain the bounds for S sigma t using this method. Okay, this is the first part. I used band limit approximation to obtain bounds for the function st. But now I would like to obtain so we start with the result of Selber in 1944. Selber, assuming Riemann hypothesis, Selber establishes this type of inequalities. There is a constant C0 such that ST is bigger than C0, and this function here. But this inequality is for infinity value of t. Selber proved this result too. ST is smaller than minus C0 log t power 1/2 over log t. These inequalities are called omega results. I will write in this form. ST is omega plus or minus log t power 1/2 over log t. This is a result by Selber. Later, Montgomery in 1977, he improved the previous result where he replaced log t to. So Montgomery improved the result of Selber, and he established that ST is omega plus minus log t power 1/2 over log t power 1/2. Nice. But recently, Bondarenko and Saib establishes the following result. Assume Riemann hypothesis, fix a number between 0 and 1. So there is a positive constant C0 such that you have this inequality. The supremum of ST in this interval is bigger than C0 and these factors here. Okay, so, and this implies that ST is omega. In this case, no, it's not omega plus or minus, it's just omega because here we have the absolute values. Omega log t power 1 over 2 log t power 1 over 2 over log t power 1 over 2. This is a result of Soundararajan concept. Recently, concept, now we can remove these absolute values here, and now we can prove this result. Similar as the result of Soundararajan concept, but now without the absolute values. And this result, I forget something here. Here is supremos plus and minus. We proved both results, plus and minus. And this is exactly the result, and this is exactly the omega result. So this result implies that ST is omega plus minus log t power 1 over 2 log t power 1 over 2 over log t power 1 over 2. So really we have now an improvement of the result of Montgomery with a factor log t power 1 over 2. Okay, I would like to give an idea of the proof. The idea of the proof is using a version of Soundararajan concept, a special version of Soundararajan concept. The idea of the resonance method is to find a Dirichlet polynomial such that you can pick large values for the function that you are studying. So the resonator RT has this form. It's a Dirichlet polynomial. It's the sum over certain subset of integers, Rm over m power it, where Rm is an arithmetic function. Let me review the idea of Soundararajan. So Soundararajan founded omega result for the Riemann zeta function in this form. Let Barphy and Smooth function with support in the interval 1, 2, a positive function, such that is 1 in this small interval. And he defined these smoothed moments, M1 RT, like as integral of the resonator with this smooth function here. He defined M2 RT, the similar integral with the Riemann zeta function here. And okay, then this implies the following. You take absolute values here. We need to remember in the points 1, 2. So this integral is defined on big T to big T. So you take maximum of this function in this interval and you obtain M1 here. This is the idea of Soundararajan to establish lower bounds for this maximum. So you divide M1 here. You have M2, absolute value of M2 over M1, and you want to optimize this ratio over all Dirichlet polynomial that are the resonators. So Soundararajan solved this problem, and he could obtain lower bounds for zeta, for the maximum of zeta. It was the idea of Soundararajan. Now I would like to review the idea of Soundararajan concept. Fix beta between 0 and 1, and take phi x, the Gaussian function. Define these sets here. This condition, you assume big T sufficiently large and let ft the number such that t plus u lie in this interval. Bondarenko side defined this moment in this form, like as integral of this set, an integral in this set of the function s t plus u ku, and multiplying the resonator with this Gaussian function. It's similar to the result of Bondarenko side in this part. The difference is that he's changing this function here with this integral here. K will be a good kernel. Now we will assume that K is a good kernel. Later I will say who will be the kernel that Bondarenko side used to establish the result. So if can take absolute values, or really no, you just need to obtain an upper bound in this form, because in this set ft t plus u lie in this interval, so you can take the maximum of s here in this interval, and the kernel q are so good, so you don't have problem with this guy. But the other part where appear the integral of f and this part is bounded by t multiplied a constant that depends of the resonator. So this is the first inequality that you can obtain using this smooth moment. But you can complete these integrals changing this f with minus infinity to infinity. And you can change this ft with minus infinity to infinity. And you need to pay this error term here. So you can change this smoothed moment here, replacing this integral with r, and you pay this error term here. And this error term is exactly the term that appears here. T and this constant depending on the resonator. Depending on the resonator. So now I would like to obtain lower bounds for this this smooth moment where you change this f with r. So we want to obtain lower bounds for this integral here, for this double integral here. So first, I would like to understand this integral here. So there is a proposition. Really, this proposition is done by Selber and used by Chang to obtain omega results too for zeta and for other functions. So, assume Riemann hypothesis, again, if you have a good kernel, so this integral of this function has is exactly this. It's 1 over pi and this imaginary part of this series here that depends on the Fourier transform of your good kernel here, plus an error term. So the idea is to replace this integral here with this series. And now the main goal of the resonator of Bondarenko side is this result. If you have a series in this form with all terms am, these coefficients here are positive, so this integral of this series multiplied with the resonator and the Gaussian is bigger than this inequality here, this factor here. A constant, this behavior log t power 1 over 2, log t power 1 over 2 over log t power 1 over 2, this minimal over this coefficient here, number depending of the resonator, and again this factor t and this constant depends of the resonator. Okay, the idea is the following. I will use this series here. I will write this series here. So you can, because this is real numbers, the resonator power, the modulus power 2 and the Gaussian is a real number. So you can remove the imaginary part here. And you have exactly a series. Well, you use Fourier theorem. Sorry, you maintain the sum here. So you have this sum, von-Manuel function, this factor here, these constants here, and this resonator and the Gaussian here. And this is exactly this lemma, because you have this series, the resonator and the Gaussian. So we are close to use, but we need to see the condition of this lemma. We need to have an such that are positive, are not negative. So if we want to apply this lemma, we want to use a good kernel such that the Fourier transform has a specific behavior. Another problem is that you have the imaginary part here. And this is a real number because it's bounded by a positive number. So we want to obtain a good kernel with certain decay analytic such that the Fourier transform is not a real, it's an imaginary pure number, because in this case, you write I, the imaginary part of this I something, showing a real part or something, and you can apply this inequality here. For this reason, Bondaren concept using this kernel, they use kx in this form, minus log t, Gaussian evaluated in this point. This is the kernel that Bondaren concept used. You obtain this number I, this constant, log t, this chi, and the Gaussian function evaluated in this point. And when you evaluate in log m over 2 pi, so this number, log m over 2 pi, log m over 2 pi, so these numbers are positive. For this reason, you can use this lemma here, because these coefficients here are positive. And then you can make the calculations, and you need to use the property of the resonator and the Fourier transform scale. Then I will use this lemma here, and in this case, this minimum of AP is bigger than a constant. So finally, this integral that we want to bound is bigger than log t power 1 over 2, log t power 1 over 2 over log t power 1 over 2, multiply t and multiply this constant depending of the resonator. And now you will see that you replace this moment t, this constant, t, this constant. In this part, t, this constant, and you kill all this part, and finally you can obtain that this maximum of this function here is bigger than exactly this this function here. Log t power 1 over 2, log t power 1 over 2 over log t power 1 over 2. So this implies the result of Bondaren concept. Now, in this case of Bondaren concept, you can see that he take absolute values here to obtain a bound in this part. So for this reason, you lost information about the sign of ST. So now I would like to construct another special kernel. This is part of the work with Kamal Mahatab. I would like to construct other kernels different of the kernel of Bondaren concept. the sign of the function of st. Take the large values and large positive values and large negative values of st. So I would like to start with this lemma. This lemma, you can prove this lemma using integration, quantum of integration. Assume Riemann hypothesis, fix a number beta and zero, between 0 and 1. Take alpha and h, these numbers. Take t in this interval, t beta, t log t. And then you can obtain this quality here. This is similar as a proposition that I mentioned before. This integral over log of zeta in this point, multiply this kernel here is this series and error term. You can see that it's similar of Selber and Sun. But in this case, you have this the logarithm function here. You have this weight here, that it is weight depending of alpha and h. And it's similar as the previous result, right? Because you have like this part, like this series here. So in some sense, it would be very nice if this kernel helps. But the problem is that with this kernel is that you don't have exact information about the sign of this part because it's a complex number. So we will do the following. I will use this identity, plus or minus 3 minus 2 sine of this part is plus or minus 3 e power 0 plus I, and this difference here. And I will apply this lemma for each part, this, and this. So in the first part, we take alpha like a log t over 4 with h0, h log t, and h minus log t. If I use this part for alpha log t over 4 and h, for instance, 0, 0, log t, and minus log t, we have three series. But this function here is very nice because if you take alpha log t over 4 and h minus log t, this weight is 0 because you have a negative number here. So this maximum is 0. So with this election alpha, this, and h in this form, this series disappears. And now we have two series with h equals 0 and h is log t. And in this case, when h is 0 and alpha is log t over 4, but this series using the pre-number theorem is bounded with this factor, log t power 1 over 4. And finally, this the series that appear with this alpha log t over 4 and h log t appear here in this part. So what I am saying the following: this integral here of the logarithm of this kernel here multiply this function here has this form, p over 2, this series, and the error term. It is very nice because we don't have two series, we have just one series. This is the reason that we wrote this number over 4, because with this number over 4, this series that appear in this part goes to the error term. the error term. So this is the kernel that I would like to use to obtain large values for ST. Well, here is logarithm of zeta. You take the imaginary part, and if you take the imaginary part, you obtain S here. So you obtain this part. The imaginary part of logarithm of zeta is st plus 1. You have this part. And again, this is I multiply this series. You take the imaginary part, you return for the real part of this series plus the error term. So now I can continue with the idea of Soundararajan concept using the resonator. I multiply with the resonator and the Gaussian. I do the integration in this part, and I can make the computation. But what's happened with this part, right? Because in the case of Soundararajan concept, they bound this smooth moment with this part with absolute values, right? In our case, if you can take 3 minus 2 sine. This is a positive function. With this sine power 2 is a positive function. So this part of the integral is smaller than of max. So you don't lose the sign of ST. In the other case, when you take minus, you have minus 3, minus 2. So this minus, you move for ST, and then you can obtain minus ST plus U with this integral is smaller than the maximum of minus ST in a certain interval. So this is the main goal here. We can construct a certain kernel such that it's always positive and always negative. And we can obtain the sign of this function ST. Okay, finally, I would like to talk about the extension of this result for SNT. For ST, we have this bound. The first bound using bandlimited approximations. These omega results. Of the function ST by Selber in 1946, where he established the result here. But Littlewood and Selber investigate the behavior and the power of cancellation of ST using certain functions, the function SNT. So, setting S0, S0 is the function S, and you define SNT as the integral of Sn minus 1 plus a specific delta. For instance, S1 is the integral of S plus a specific delta. S2 the same. Is the integral of S1 plus delta. Littlewood and Selber, they don't mention why they define these functions. But for instance, we can use integration by parts to relate this function Sn with the zero of zeta. For instance, if you define nkt with the imaginary part is smaller than t, and using the Riemann von Mangold formula, using integration by parts, you obtain n1, and this n1 has this form, this part, and in this moment appear this function S1 here, plus the error term. For instance, for N2, you use integration by parts again, and here appear S2. So, for instance, in this equality here, you can use the von Mangold formula again, Riemann von Mangold formula again. So if you define N1 star T, you have these sums here. It's similar of the Riemann von Mangold formula, but now appear S1. Not S, just S1, only S1T. These functions are very nice in this part. We have similar form. The Riemann hypothesis is equivalent to have this decay. SNT is bho power bho t power n minus 2 for any n bigger than 3. So for this reason, we want to study this function SNT. Again, Littlewood, when he established the result for ST with this behavior, he established the result for all Sn. So Littlewood, assuming Riemann hypothesis, he proved that SNT has this bound, Cn plus an error 10 goes to 0, log t power log t power n plus 1. And the idea is to optimize this constant here, Cn. For instance, when n equals 1, we have the result. We have the result of Littlewood here. And I would like to know the constants. Karasub and Korolev show with this constant 40 and minus 40. Fuji improved this result with this constant here. And finally, Caneros and Milinovic, using this technique of band limit approximation, they proved these results with this constant, P over 48. For the case n bigger than 2, we have the result of Wakasa. Wakasa establishes this inequality of Littlewood with this constant here. These sums, depending of these factors here. And in particular, his constant Cn goes to this number 0.3203. Using this technique of band limit approximations, solving this Bell-in-Server problem, we can establish the result. For SNT, we have upper bound and lower bounds as Littlewood, but with these constants. In this case, for instance, when n is 4k plus 1, you obtain Cn plus here in this form, depending on value of zeta. You have lower bound here too. In the case of n is 4k plus 3, you invert the result. When n is even, you use the combination of Cn minus 1 and Cn plus 1. This is because you and we can obtain information about S using the bounds for S1 and S minus 1. Here is a similar. If you want to obtain bounds for S2, you need to use the bounds for S3 and S1. Because we are defining Sn is the primitive of Sn minus 1. This constant are very nice because now this constant Cn, this constant is going to 0 with exponential decay. So we improve the result of Wakasa here. In another hand, about omega results, Bondarenko and Saib showed this result. Assuming Riemann hypothesis, they showed that S1 is omega plus this behavior here. Log t, log t, power 3 over 2. And this is an improvement of the result of Zhang. Zhang has this result without this log t power 1 over 2. And using this kernel that we obtained with Mahatat, we can extend our result for all Sn. So when n is even, you have that Sn is omega plus minus and has this behavior. But with this denominator, log t power n plus 1 over 2. In the case of n is 4k plus 1, we only obtain omega plus as the result of Bondarenko side in the case n equals 1. In other case, n equals 4k plus 3, you obtain omega minus here. Until now, we are thinking how we can obtain here omega minus and here omega plus. It's not clear for us because we need to change a kernel now. Well, and finally, to talk something about the moment of Sn, a classic result of Littlewood established that the second moment of Sn is big OT, and in a recent result, with Oscar Quesada Herrera, we establish the constant here with the constant as this constant has this form, this series here. So finally, similar as the argument function st, now we have this result for Sn. Bounds for Sn using bandlimited approximations, and omega result for Sn using resonance method. And the second moment too. Okay, this is the talk. Thank you so much for your attention.
Thank you very much, Andrés, for the nice talk. So we have time for questions. Does anyone has a question? Well, I have a question. So in one of your results, you remove the modulus of the theorem of Bondarenko and Sipe, right?
Mm-hmm.
And then you take the sup. So perhaps a naive question, what can we say about the infimum of the negative part? Will have the same magnitude, order of magnitude?
Really, I don't know, because if you want to take an infimum, you need to construct another resonator such that you can obtain upper bounds for these certain smoothed moments. Really, I don't know. I don't know if it's possible to obtain an infimum of t in this interval.
Mm-hmm.
Yeah, it's not clear for me to obtain this infimum.
Okay, Andrés, thank you very much for the nice talk.
Okay, thank you so much for the opportunity.